We experience our devices as instantaneous. You tap a screen, and a high-definition video plays immediately. But beneath the glass, inside the microchips running those apps, the hardware is bound by strict physical limits. The brain of your device is the central processing unit, or CPU. It executes the billions of microscopic instructions required to make any software function. Every single instruction must pass through a rigid 4-step cycle: fetch, decode, execute, and write back. First, the processor retrieves an instruction from memory. Next, it translates that instruction into an operation code it understands. Then, the arithmetic logic unit performs the actual math. Finally, the processor saves the result. Historically, this entire process operated in a single physical dimension. A processor handled exactly one instruction at a time, forcing every 4-step cycle to finish completely before the next one could begin. This strict sequence creates a massive inefficiency. While the execute unit works, fetching and decoding components sit idle. Processing sequentially leaves huge gaps of empty time where the hardware does nothing. Engineers tried brute forcing the problem by pushing electrical signals faster, but running chips at infinite speeds generates intense thermal energy, eventually melting the silicon. To meet modern software demands, chip designers stopped trying to outrun the clock. Instead, they manipulated the flow of time so no part of the processor ever sat waiting. The solution was pipelining. This architectural leap upgraded the CPU from a single file line into a 2-dimensional grid. This diagram illustrates overlapping instructions. At cycle 1, the CPU fetches instruction A. In cycle 2, it fetches instruction B while decoding A. Fast forward to cycle 4. The processor is decoding C, executing B, and accessing memory for A, all simultaneously. This does not speed up any individual instruction. Instead, it maximizes throughput. Once this pipeline is fully loaded, the processor outputs one completed instruction every single clock cycle, rather than one every 4. By stacking operations into a grid, pipelining folds time. The processor overlaps workloads so every physical sector of the chip is active at all times. Even a perfectly packed pipeline eventually hits a physical wall. A single processor can only handle so many overlapping instructions. To scale further, the architecture had to move into 3 dimensions. This block diagram compares a standard single-core processor on the left to a modern multi-core processor on the right. A multi-core CPU integrates multiple independent processors, called cores, directly onto a single silicon chip. This creates a multiplier effect. Each of those independent cores contains its own fully functioning internal pipeline. This allows for independent execution. The computer's operating system assigns completely different tasks to different sections of the chip. Core 1 might run a web browser, while Core 2 handles a background software update. Alternatively, the chip uses parallel execution. A single massive mathematical workload is divided into pieces. Each core takes a fraction of the data and processes it simultaneously, cutting the total completion time in half or more. Running multiple pipelines simultaneously requires strict traffic control. Because the cores share the same memory pool, they rely on protocols called cache coherency. Cache coherency ensures cores constantly synchronize their data access, preventing them from overwriting or corrupting the information they rely on. Combining the temporal overlap of pipelining with the spatial division of multi-core processing turns the CPU into a synchronized 3-dimensional industrial matrix. Looking directly at this physical gold-pinned chip, it is easy to view it as a single static object, but the surface hides a sprawling microscopic factory. Modern hardware has long bypassed the bottleneck of processing a single logic gate at a time. By continuously scheduling pipelines to eliminate idle time and multiplying the cores to bypass physical speed limits, computer architecture achieves massive scale. The power of our devices rely on this microscopic choreography. They manipulate time and space so machines can do almost everything all at once.